Okay, welcome to HAO Colloquium. Our today's speaker is Alberto Marcos Vasquez from Institute for Astronomy and Space Physics. It is my great pleasure to introduce Alberto. Alberto completed his undergraduate studies in physics at the University of Buenos Aires, Argentina, and later earned his PhD in physics from the same institution. He conducted his PhD thesis research for 2 years at UBA and then 3 years at the Harvard Smithsonian Center for Astrophysics under a Smithsonian pre-doctoral fellowship, focusing on modeling various physical phenomena in the solar corona. After obtaining his PhD, he held a postdoctoral position at the Institute for Astronomy and Space Physics, which is affiliated with both CONICET and UBA in Buenos Aires. Later, he became a research scientist at IAFE, where he has been working for about 20 years, collaborating with colleagues from Argentina, the US, Europe, and Asia. His current research mainly involves studying the solar corona on a global scale using tomographic techniques with the aim of addressing open problems in solar corona physics, such as coronal heating. Alberto has a passion for teaching at the university, where he has taught for more than 25 years, mainly to physics undergrad students and currently to students of environmental engineering. Outside of academia, his primary interests include listening to music, improving his sound systems in a seemingly endless fashion, cooking and eating, exercising and getting as much sleep as possible, and playing with his pets, Argos and Wilson. So today, Alberto will be speaking on solar coronal rotational tomography, diagnostics, and applications.
Thank you so much. Thanks for inviting me. Happy to be here. So let's see how do I put this here. There you go. So probably this is no introduction, but we are focusing on the coronal part of an atmosphere. This is our objective with solar rotational tomography. Needless to say, the importance of the corona in understanding the Sun-Earth environment. Coronal images in optically thin ranges, such as UV and white light, are two-dimensional projections of three-dimensional structural emissivities. And of course, understanding the 3D thermodynamical structure of the corona from observational point of view is essential to advance models. Here I just mentioned there are different techniques to infer three-dimensional structure in different scales. So, for example, UV stereoscopy allows to determine the three-dimensional shape of magnetic fields in active regions, simultaneous observations from 2 points of view. And in tomography, what we do is to determine the three-dimensional emissivity structure from sequences of images. So when I talk of tomography in this context, what I mention or tomographic reconstruction, what I mean by that, what we mean by that, is given some quantity X that is unknown, such as, for example, the electron density in each cell of a tomographic discrete grid in the corona, observed under an optically thin regime, such as, for example, white light. This is the unknown. We want to reconstruct that, and the knowns are the intensity measurements in each pixel of each image. We can construct a very long vector of data points, and then a projection matrix that depends on both the geometry, solar rotation, the telescope orbit, and the eventually physical process such as Thomson scattering. solar rotational tomography, the object of study is the corona, and the way we obtain the different points of view to constrain the inversion problem is to allow for the sun to rotate, basically. This changed recently. I mean, with a mission like Parker, we can really, the orbital movement becomes a big part of going around the sun, not only the sun rotation. So originally, tomography was developed for the K-corona, for the white light continuum. That's a diagnostic of coronal electron density through some Thomson scattering. So by doing SRT, solar rotational tomography in white light, one can obtain three-dimensional reconstructions of the electron density of the corona. So more recently, if you tackle the E corona, you have the EUV instruments that pick up lines that are excited, iron lines basically, excited by collisions with free electrons. And by doing solar rotational tomography with EUV, we obtain three-dimensional maps of the emissivity in each band of the EUV instruments. We call that the filter band emissivity. And then on the next step, after doing tomography with the several bands, we use that to do a three-dimensional TEM analysis. That is a TEM analysis within each individual cell in the corona. I'm mentioning here probably the first paper with solar rotational tomography. These are the original papers with the EUV case. So this is just the list of the instruments that we have been using for SFT, both in white light and EUV. Mainly LASCO-C2, we have used limitedly Core 1 maybe, then AAA and UVI, of course, and on white light mainly LASCO-C2. Then from ground-based coronagraphs, we have used MK4, at least a couple of times, K-Core, as we've been discussing, and now the new instrument that we are using is UComp. We're going to talk about that later. So the general idea is we set up a spherical grid in the corona. Just to give you examples, if we're talking of white light, we are looking into the inner and middle corona, depending on the instrument. With K-Core, we can see the inner corona, a little bit of the middle corona. With C2, we see the middle corona. Just so you have an idea, in C2, the field of view is 2.5 to 6 point solar radius. And typically, a voxel, which is one of these grid cells, will have this size: 0.1 solar radius in the right direction, and 3 by 3 degrees, or 4 by 4. It depends. So we basically will use 14 images. So the number of pixels is of the order of 10 to the 6, and the number of voxels, that again depends on the field of view. For the C2 case, this is a typical number, 10 to the 5, right? In the case of EUV, this is our field of view with any of the instruments, CNT, UVI, or AAA. And our voxel size is typically this one here, and these are the typical numbers for the number of voxels and pixels. So this is the problem to solve. The signal that is recorded in the jth pixel is basically a line of sight associated with that pixel. There is this unknown, x, and then some weighting factor. And once you discretize the problem, you have a large linear inversion problem. You have a y vector with all the intensities measured in every pixel of our image. Then you have a large sparse matrix of j times I elements that is purely geometrical. And then you have an x vector of unknowns. So in these equations, everything that is blue is known, and everything that is red is unknown. So as examples, in case of white light SRT, the x is the electron density, and there is a weighting factor there, which is the Thomson scattering factor. And then in the case of EUV solar rotational tomography, the unknown is a filter band emissivity that we call E in this case, which is basically an interval in the wavelength of the spectral emissivity of the corona times the passband. And there is no weighting factor here. So basically what we end up is, but the way to solve this problem is to make essentially a big least square fit, right? We look for the unknown X that best reproduces all the images in the time sequence. Basically, A times X is the synthetic images values, and Y is the data. So it's basically this. How do I go back? Perfect. This is a sparse, very big matrix, and that's prone to high frequency artifacts if you don't do anything else. As in any other demographic reconstruction, you try to impose anything that you can on the solution, such as positivity in this case, or certain smoothness. So we call that regularization. It's basically a matrix of derivatives. So to kill artificial high frequency spatial gradients. So once you do that, just as an example, as a first example, we have time series. I just put 2 here of K-core. And the result of doing white light tomography will be maps of latitude and longitude of the electron density at several shells. I'm just plotting here at one height. Similarly with C2, let's say, we obtain maps of electron density. These are just one shell at one height as an example. So once you have your tomographic reconstruction, what you can do is take images, actual images within the time period that you analyze, and use your reconstructed electron density to compute synthetic images. So this is one of such examples. So on the left, you have a true image by LASCO, and on the right, you have the synthetic image obtained from the tomographic reconstruction, and you can do that for other images, of course. As you can see, typically the match is very good. I will show some histograms of analyzing this, how they compare the true image and the image produced by the tomographic reconstruction as a movie, which is pretty neat. So thanks for the mic. Yeah. So that's the output of white light tomography. In the case of EUV tomography, for example, here you have one of the images of the time sequence of maybe a validation image. And these here are examples of shells of the reconstructed emissivity for the 171 band, just picked at some heights within the grid, let's say 1.03, 1.1, 1.15. You have then a mamushka, spherical mamushka, right? You have like 25 of these, and you can compute synthetic images as predicted by your tomographic reconstruction. So the same happens with the other bands. But these are 3 independent tomographic reconstructions. We have one for the 171 series of images, a different one from the 195, and another one from the 284. So we have 3 tomographic products in this case, right? 3 three-dimensional NCAR structures. Like with white light, once you have your tomographic reconstruction, let's say, for example, in 193, you can take real images and compute. You use the header to obtain the exact geometry of the observation, and you compute your synthetic image. This is just a comparison of a real image in 193 and the one predicted by the tomographic reconstruction. Again, there's a movie here, I guess. Or probably I can just advance one per one.
The big triangle.
Yeah, next movie. But I think it's nice to see, yeah, so you keep control on the speed. As you can see, you can recover pretty fine features, which is, of course, expected because you are constraining the problem with the real images. And that's a movie. Again, I'm going to show a couple of cases with histograms, just so you see the ratio of synthetic over actual images. So that is what you get with EUV tomography. You get these three-dimensional reconstructions of emissivity. Now, what you can do with that is a three-dimensional version of a DEM analysis. So instead of obtaining a DEM, you will obtain a local. Instead of being the DEM describing the plasma along the line of sight, it will be the DEM within each tomography. So of course, the signal measured in each pixel of each band is the integral of the specific intensity times the passband, and the passband for each instrument will give you the temperature sensitivity, right? If you have a temperature response, this is, for example, one for EVI. So, as you know, these are not, these have a peak on certain temperatures, let's say 1 million, 1.5, 2 million, and then some spread around that. That's the sensitivity. So at this point, for each band K, we know the filter band emissivity A, K, I at each tomography voxel I, right? So let's fix the K. Let's say 171. We have one emissivity at each voxel. And using the temperature response, these filter band emissivities can be written as a temperature integral within the voxel, which multiplies the response function tau times the local differential emission measure. And again, here, everything that is in blue is known, and what is unknown is the LDM. So the LDM is defined in such a way that its first moment is the squared electron density, the average squared electron density within the voxel. Then the next moment is the temperature, and you can have also a spread in temperature within the voxel. So, we only have 3 data points typically with instruments. With AIA, we might bring that into 4. But typically, we use 3. So in each cell, what we do is we have 3 emissivities. We just model the local DEM, let's say, for example, as a normal function with 3 free parameters. And we basically make, again, a least square feet within the cell now. This is post-tomography. This takes into account the 3 emissivities that we reconstructed. Now you find the single LDM that best predicts the 3 emissivities, the 3 bands. So once you find that in each voxel, you can construct maps of, for example, electron density or electron temperature. So here you have just an example of, for some rotation, a map of electron density at some height. I indicate here a few voxels. Let's say, for example, 1 here in the coronal hole. What you are seeing here, is, of course, is a streamer in red. And there you're changing. This is a solar minimum analysis close to it. I'm pretty sure this is the WHI. I think it was that. So let's say, for example, in 1, your LDM will be this one. And for example, in 4, it will be this red one. So you're looking at the less dense and colder cell here, and you're looking at the larger, denser, and hotter cell here. The average temperature would be the centroid. Actually, the average, not the centroid of the LDM. So, as a summary, once you have done EUV tomography in the 3 bands, you have 3 three-dimensional emissivity maps, and you combine those into a local DEM analysis, and you can hope to reconstruct density and temperature. This here is
a quick question.
Yeah.
What are the black
regions? Okay, so the main limitation in solar tomography is dynamic. You need a sequence of images, right? Typically taken over, let's say, for an instrument like AIA or EVI or C2, you need typically 14 days. You need half rotation of the sun. You block the sun, and you need to see the whole corona. So you need 14 days to have line of sight, so probe all the coronal volume. There will be dynamics going on. Now we are assuming a static corona over a period, so we need to find a single static structure that is able to explain the best it can all the sequence of images. If at some point during the data acquisition time there is some structure changing, brightening up, for example, SRT needs to explain that purely in terms of a change of perspective. So it strategically places negative values, for example, which bring down to zero. So those will be artifacts in the reconstruction. So with SRT, you aim at reconstructing the middle to large scale corona, the most stable part. So for a given longitude, and there might also be darker regions in the case of EUV tomography specifically, because, for example, you might lack signal in the hotter band. The localization of artifacts due to dynamics in the case of EUV tomography combine the artifacts of the three independent tomographies, right? What is important to understand is also that a given longitude is typically seen in the time series only if one or two images, well, that structure passes the limit, right? So if that structure is evolving afterwards, we don't have any information on that. So we don't solve for that. This is pretty similar to what happens, I think, with synoptic magnetograms feeding 3D MHD runs, right? You need to construct a full magnetogram using a time sequence of magnetograms. There is no way out of that. There are schemes of time-dependent tomography developed here. I remember the Marc Boutala case, and in France, the Didier team. In the end, the results are pretty similar to static SRT. The reason being that we basically rely on one single point of view. We have done tomography with 2 points of view using UVI, for example, but we don't gain that much. It would be great to have a fleet of exactly equal instruments around the sun, not only for tomography, for a lot of things, but that will benefit tomography a lot.
May I ask a
Sure.
question? How well do you know the heights of the structures in AIA on the disk?
Say that again?
You had synoptic maps at different heights. You're displaying one of them there. How well do you know the height of the structures in EUV on the disk?
Well, we block the disk actually. We are not using
this is all getting gleaned from the lab.
Yes.
Okay, thank you.
In the beginning, we have used the disk as well, and we have made comparisons. If you do EUV tomography using the disk, which you might do, because it's purely coronal emission anyway, there's no reason in principle to block the disk for EUV tomography. And in the beginning, we didn't. Okay, so if you block it, first advantage is you only need half the time. Half synodic rotation is enough. If you don't block the disk, the first thing to do is to use a full rotation. First thing. Second, by blocking the disk, like I said, if some structure is evolving, as long as it's stable, when it goes around the limb, it won't introduce artifacts in the reconstruction, as opposed to using the full disk that you are absorbing all the dynamics. So, but it's not as terrible as it sounds. When we changed from disk to full limb tomography, we have done careful comparisons. What you actually are doing, you're reducing the number of artifacts due to dynamics, and you kind of obtain a more smooth solution. You are not feeding your tomographic inversion with fine structures seen on the disk. So, so the next one thing is, in these maps, I'm showing these black curves here. Those black curves are the open-close boundary from a PFS model of the same period, which, as you know, is a totally independent product. In general, we see this kind of agreement. It's very nice to see the change from higher to lower densities or higher to lower temperatures pretty much along the open-close boundary. So what we usually do is to combine tomography now with coronal B extrapolations, PFSS or 3D MHD models. So we have our grid, we have our tomographic reconstructions, we have now field lines from a model, and we can trace the tomographic products on the field lines, and this is what we typically do. And then we analyze, say, electron density or temperature along the individual loops. And these analyses are typically done in a statistical way, of course. We don't rely on single field lines or just specific boxes, tomographic reconstruction. But we are, by combining with a magnetic model, we can hope to analyze statistically different coronal structures, say the streamer, the coronal holes, etc. This is just an example of that. It's surrounding corona. This is a PFSS model exactly of this eclipse, which I don't remember right now which one it was. And these are the reconstructions for that period. For example, at 2 different heights, I'm showing here in the grid maps of electron density and electron temperature. Again, the thick lines are the open-close boundary of the model for that period, the magnetic model for that period. So just as an example of result, this is back in 2012. Shang Huang and collaborators, they analyzed these tomographic results along closed structures within the streamer belt. What we found is structures with temperature increasing with height and structures with temperature decreasing with height. We tap them back then up and down loops. So later, after that work, we took this solar minimum back in 2008, 2010, and we analyzed a series of rotations with tomography. And what we found, this is a map of the location of the down loops in blue. So these 3 rotations, for example, are towards the deep minimum. So this is farther from the minimum, this is closer to the deep minimum, this is right in the deep minimum. So what we found, and this is the structure you can see here, for example, the open-close boundary, we are advancing to a much more organized kind of dipolar corona. These are beta maps. We can use the density from the tomography and the model magnetic field to make maps of plasma beta. And we found that these down loops tend to be located in regions of larger plasma beta. A few comments on that. So here, for example, you have those rotations that we analyzed. This is the transport number. And this in light blue is the fraction of down loops. So back then, what we found is that these down loops are characterized with beta of the order of 1 or even larger, and up loops by beta smaller than 1. And I remember then that Steve worked on this. They did 1D MHD models with time average heating rates, and they reproduced down loops if mode conversion is highly efficient. I remember that was your result. So this is just to give an example of the type of results that we can provide with tomography. As you all know about the solar cycle. So we have analyzed with tomography the 3 last solar minimum using EIT, EVI, and NIA, picking specific rotations from each of those minima. This was a series of work by Diego Rivera's collaborators, and this was his PhD thesis actually. So here you have a few examples of reconstructions of density and temperature at a specific height, just not to put too many plots for the 3 different rotations. I just want to highlight that we've been using the 3 available instruments, right? Another study has been, for example, to analyze what are the characteristic temperatures that we derive from DEMT, differential emission meter tomography, using AIA, and including the hotter band. We were talking all this earlier today. When you use 3 bands, typically a normal model will do very well. By do very well, I mean that the LDM you obtain in every tomography voxel predicts very well the 3 emissivities that you obtain with tomography. When you add a 4th band, 335, it's a hotter band, but still captures. It still has very significant emission in the quiet corona. So when we do that, we found that we tried several different parametric models. This is totally free, of course. But what we found is that any model that reproduces reasonably well the 4 emissivity in this case will have always the same electron density and average temperature. There is not a single model. For example, we can use a 2 normal model, which is this blue one, with 2 populations of different plasma, or we can use this asymmetric top hat, for example. So what I'm showing here is for a specific cell, using the 4 emissivities produced by tomography. These plots are showing the best each model can do to predict those 4 emissivities. When you analyze this in the whole corona, using the same color code, blue here is the binormal distribution. This is a ratio of the synthetic emissivity as predicted by the tomography reconstruction and the tomographic reconstructions. So the binormal is the best one in terms of predicting everywhere the observed emissivity in 3 dimensions. And when we then analyze, we obtain those bimodal distributions. We obtain a couple of characteristic temperatures all around the quiescent corona. And interestingly enough, those numbers match very well EM analysis of spectral data from quiet regions. So there's a nice review by Feldman and Lange where they find 2 characteristic dominating temperatures in the corona that match pretty well the ones we get with DEMT using 4 bands of AIA. I guess I will try to accelerate this. Here's another series of studies. I will mention the first one in this series by Cecilia McCormack and collaborators. So we took the loops modeled by the PFSS or 3D MHD, and assuming a simple balanced, steady balance of heating, radiative loss, and conduction losses, we can integrate that equation within the flux tube, each flux tube, and come out with an integral version of that energy balance. So in this equation here, let's say on the right, of course, the heating, this is the heating, this is the energy flux is pH needed at the coronal base to maintain the whole loop stable, thermodynamically stable, to exactly balance the radiative losses and conductive flux. So in the right term, everything that is in white is known from the B model. It's a model, of course, either PFSS or 3D MHD, but that's the magnetic model. And everything in blue or green is derived from the tomographic reconstruction. You get it from the density and the temperature that you reconstructed from the tomographic reconstruction. So by combining DMT with the magnetic models, we can make maps of pH, which is 2-dimensional maps of the energy flux required at the coronal base to maintain these loops stable. Here are the details of how you compute the radiative power from the DMT or the conductive flux. But at the end, what you have, I mentioned before, these down and up loops. These are the down loops, these are the up loops, and we basically obtain these red histograms of the energy flux at the coronal base needed to maintain each loop in in an equilibrium. So the histogram is because we are analyzing here, I don't know, thousands of these fluids throughout the whole reconstructed corona. So typical numbers are in the order of 10 to the 5 ergs centimeter square per second, which are numbers consistent with this analysis by Han and Savage, spectral analysis of interpreting the non-thermal broadening as, for example, coming from alpha waves, just to mention a comparison there. Actually, this was done by Cecilia McCormack, and then repeated that study with Diego Lloveras later on. We obtained very similar values for other rotations. So I'm mentioning maybe first works in some of these lines and then some subsequent works for other periods. Another use of this has been over the last 10 years or so, the use of these tomographies to validate runs of the energy models, particularly, as you know, we are working close to the Michigan group. So we have been validating their awesome model runs. I'm mentioning here a work by Iran et al. I think this is the first we did with validation, some more 10 years ago. So for example, here, these rings that you have are, these are temperature maps, these are density maps. So these rings are showing, this is 1.0 to 1.25 solar radii. This is the range we reconstructed with UV tomography. So this is the ratio of the electron temperature from tomography and the model. So anything that looks green is closer to 1 in the ratio. We have been using then these results also to validate their slow fast wave transition models. We have been using the reconstructions for that. And the latest validation study has been done by Diego Lloveras and collaborators a couple of years ago with the latest implementation of the awesome model. For example, here you have a few plots of electron density as a function of height. Solid lines are the tomographic reconstructions. Dashed lines are the model. These are average trends for different regions. In this case, the orange curves correspond to the core of the streamer. The red curves on the edge of the streamer, and the cyan, you say, curves, these are in the open region. The same here for temperature. So typically we are having this kind of agreement between electron density and temperature between the tomographic reconstructions and the model, which are around the error bars that we have. Typical error bars from tomography are of the order of 5 to 10% in density and temperature, accounting for the two main sources of error in tomography that we can estimate, which are calibration, radiometric calibration of the instruments, and the regularization of the solutions. Okay, so for example, here's from that work an example of AIA images 171, 183, and 211. These are the real images. These are the synthetic images produced by the tomographic reconstruction, and these are the synthetic images produced by the run of the awesome model for that synthetic. And here you have the histograms, right? These are typical comparisons. So this is synthetic tomographic images over the data, and these are the awesome images over data. Of course, the match of the tomography is expected to be better because the tomography is produced exactly to do that job. You know, with models, of course, you can have more or less success for the image. So this is just one example. In that same work, we also we did simultaneously the EUV reconstructions in the inner corona and the C2 white light reconstructions in the middle corona. So there's also comparison with the also model at larger heights. This analysis was done for the WIPI campaigns, couple of WIPI campaigns. For example, here you have a map of the electron density reconstructed from C2 at 2.5, and the white lines are open close boundaries at that height from the OSOF model. And okay, this is the result of the electron density of the OSOF model. As another example, here you have a LASCO C2 PD image from that period. Here's a synthetic image produced by the tomography, and here's the one from the model, and here are the ratios of the tomography over the data and the model over the data. No surprise, of course, the match with the tomographic image has to be better. Just a summary of current projects that we are working on that use both white light SRT and differential emission vision tomography. So I came here from Michigan. We are working with Enrico Landi and Tracy and Federico Nuevo on using tomographic reconstructions. We're working on determination of solar wind speed as a function of height in the inner corona. So below 1.5 solar radian. So the idea is to use the tomographic reconstructions of electron density and temperature in the inner corona as a constraint in the source region of the wind, and then combine that with in situ charge stage measurements at 1 AU, connect both with the 3D-dimensional NHD simulation, and use the ionization equilibrium code around those field lines. And Monte Carlo methods are applied to a parametric model of the wind along the field lines constrained by those two data sets. So that's one application of tomography that we are pursuing right now. Another project that I want to mention is the observational validation of CMEs with the Space Weather Modeling Framework. So, of course, tomography is oriented for non-dynamic events, but still can be used to analyze winds in the sense that, for example, with the Space Weather Modeling Framework CME simulations, you basically need two models. You need the OSOM model to model the background corona, and then you use the EGL model to simulate the CME event. So this is led by Diego Lloveras, who's working now in Mendoza with EVE. So he's working in collaboration with us at IAFE, Chip Manchester, and the team in Michigan. So the idea is to use tomography to validate the simulations of the background corona, and to use CME observations based basically on coronal white light images to validate the simulation of the CME. So he's working on both ends. Diego right now is focusing on, by the way, on segmentation of CME images in situ and core 2 for automatic characterization of the morphology and the kinematics using neural network algorithms, which is something I think his work on that can also be used for in the future for patch images as well. So this is kind of the talk that I had prepared, but then I added what we saw in Punch. So the new instruments. So my talk in Punch was called Solar Rotational Tomography with latest instrumentation. Meaning by that, the latest that we are to use with SRT. So right now that is METIS and hopefully in the near future Punch as well. So as you know, Solar Orbiter has these highly eccentric orbits. It has two detectors in white light and light alpha, and that's very interesting for tomography. So in that meeting, I show you guys this comparison of data between METIS and C2. C2 has been kind of a reference instrument for so long. So before engaging into the tomography with METIS, we wanted to compare the data. So there was this rare, but they happen from time to time, conjunction between Solar and SOHO in 2022, late September 2022, 29th of September. So METIS was here in the red dot, C2 was here. These are the two measurements, flipped one of them so that they match structurally. You can see the same structures. Obviously, this is a nearly perfect position within less than 1 degree. And the images are really simultaneous. They are 20 minutes apart. So this is an example of PV as a function of position angle. METIS systematically sees a larger signal in a ratio of 1.662 million. The correlation is excellent because these images are, of course, simultaneous. And this is, one should try to understand what amount of this discrepancy can be due to the fact that you are observing, for example, from different distances from the sun. So when you observe the same elongation on the opposite limbs, your lines of sight are not drawing the corona exactly the same, right? There's a slight difference. But this is a simulation of that. By the way, if you switch back between the actual data and the simulated, this is an awesome simulation of the period. These are synthetic images we computed with that model, exactly replicating this observational geometry, right? In favor of awesome, the main structures are there. This is not the point of this work anyway. Any model serves the purpose. The main point is to show below you see the same analysis that we did here with the real data, but with the synthetic data. So this is showing what is the difference that you can expect to see only due to geometrical effects of observation, which are really minimal and most importantly, not systematic. Sometimes the METIS data could be slightly larger or lower than C2. At some points, you might see more difference. That's simply because I was mentioning this to you. There might be some more fine structure there. So slight changes in the line of sight are probably maybe more noticeably different densities, for example. So that's not the cause. The cause of the discrepancy is related to the calibration of the instruments. So this is an example of now tomography. So we took 3 segments of data to do simultaneous tomography with METIS as. So I think I'm showing here the third period, this segment here. And I'm showing here the tomographic reconstruction based on METIS at 2 different heights, and on C2 at those 2 different heights. So structures are the same as expected. And then if you analyze statistically the relationship between the density reconstructed with METIS and with C2, we have this discrepancy which very closely matches what is expected, of course, because of this. The difference in calibration, intercalibration between the 2 PDs will directly linearly transfer to the difference in electron density. So a nice thing of this is just a summary of what I showed you. So we really believe the problem is in, or the difference of the problem. The difference in these results is in the calibration. There's a careful calibration work being done by Alexander Boulder, colleagues of the METIS team. What I want to highlight is that we think this is a nice example of showing, your images depend strongly on the point of view, but your tomographic reconstruction should not. If you have a sequence of images long enough to cover the whole corona, it doesn't matter where you look from, principle. You should obtain the same reconstruction. So we believe it's a nice aid for comparison of calibration of instruments. I'm almost done, so I'm done. So I didn't show this in the bunch meeting because we don't really have yet the data. I'm going to show just a couple of slides on doing Lyman alpha. So Lyman alpha is optically thin in the corona, but the nice thing is that as opposed to the EUV lines that are collisionally excited, this is purely radiatively excited. So it's sensitive in principle to the wind speed, right? I won't go into the details, but you can basically express the intensity of Lyman alpha as a line of sight integral, some weighting factor. This is a dilution factor in this case of the chromospheric emission that is exciting the coronal hydrogen, neutral hydrogen, which is very little, but everything that is there, it gets excited. And it, as you know, it's a very, very dominant line in the spectrum. So when you, and there's what we call the Doppler limiter. Again, in this equation, everything that is in blue is known in principle. It's geometrical, basically, plus the intensity measured in Lyman alpha. And the unknown here is this Doppler dimming term. This is not exactly the Doppler dimming term. This is the product of NH and D. This is the Doppler dimming term. So the good thing of METIS for us now is that we can simultaneously do, so we get a sequence of white light images, we get a simultaneous sequence of Lyman alpha images. We can do independent tomography. With white light, we get the electron density in 3D. With Lyman alpha, what we will get in principle is a reconstruction of this quantity, DH. Combining those, we can hope to derive dimensional maps of the Doppler dimming term, and that in itself is an interesting product. Of course, it's a constraint on, it could serve as a constraint for models. It's a simultaneous constraint on wind speed as well as proton temperature. By making very simple assumptions right now, this is the first approach to the subject. This is an analytical expression that has several underlying significations in the chromospheric profile. We are using a asymptotic expression for the Doppler dimming effect. But in principle, combining these two tomographies with a model for temperature and wind speed, a magnetic field, sorry, one can expect to reconstruct the three-dimensional wind speed. Again, this is a very first simple approach. So here, as an example, we have done some simulations already with this, only with synthetic data. So we have a model, we're using the awesome model, we produce synthetic white light images as if seen by METIS, synthetic Lyman alpha images, and then we try to reconstruct the wind speed. There are some issues, but we can at least reconstruct the overall structure and most importantly, the change from fast to slow speed. Very, very preliminary stuff. We look forward to have the Lyman alpha data. To close this, the new instrumentation for us is HAO. These are optical coronal emission lines. So we just probably weeks ago in this visit in Michigan, we adapted the codes to digest your UCOMP images. So we make a first try at using 174 and 179. So by feeding 174 images or 179 images, what we come out with by doing tomography with each line is a three-dimensional map of the emissivity of that line. So here I'm just showing latitude, longitude maps at 3 different heights. Because of the field of view that we have with UCOMP, I'm showing here emissivities at 1.1, 1.15, and 1.2, right? So once we have this, we can do, in principle, we can apply any diagnostic that you can do with the intensity now with the NEC, right? Once you have undone the line of sight effects, now you can do a local analysis within the corona. So the first thing to do is, using the line ratio diagnostic of electron density, we constructed, and this is a new thing for us, electron density maps in the analyzed volume from the Yukon line ratio, but we did the EUV electron density reconstruction based on AAA data, and at the same time, the electron density reconstruction based on the K-core data. So these are three-dimensional reconstructions of the electron density based on three different diagnostics. We did this in a rush. The series of images here are nearly synchronic, but not exactly so, as we've been discussing. So there might be a difference of 1 hour or 2 hours. But we start on a good English, because we see the same structures, of course. I won't get into details now of the different reasons for the different unreconstructed regions. And here is a histogram of the ratio of electron density throughout the whole volume from Yukon and AAA. This is a global average radial profile from Yukon and AAA. And this is the same comparison between Yukon and K-core. This match is remarkable. And this difference, we seem to have brought it down a lot. It had to do with the K-core units that we were assuming were in the images. It seems that it's different than we thought. And by doing that change, this will be brought down by 20%. So that's very nice. Closing comment is that the emission lines to which both Yukon and AAA are sensitive are produced by ion ions. And while the field line ratio diagnostic of Yukon is independent of the abundance of ion, the electron density produced by EUV tomography, DMT tomography, is actually proportional to 1 over the square root of the iron abundance. So in principle, these differences could be an indication of, I should mention that when we do the DMT tomography, we are assuming a coherent abundance of the Feldman set. So 4 times the photospheric level. This is the post-tomography analysis. So this can be changed locally in Excel, and by comparing these two reconstructions, we might hope to bring some three-dimensional constraints on the distribution of iron abundance. And I mentioned before that this K-core difference, we have done previous comparisons of K-core electron density from tomography K-core electron density, DMT for other periods. And the differences were very comparable to this. But again, a lot of that needs to be now readjusted from what we just learned about the units of K-core. So that's very nice. And I think our next step with this will be then to pick 2 or 3 different periods where we have very good Yukon data, fully synchronized, right? Because here we have this beautiful thing that Yukon, AAA, and K-core are looking at from exactly the same point of view, distance to the sun, so there is no need to introduce noise by not having simultaneous images. So that would be the next step. And that would be the first step towards something that we've been thinking with ridge tracing and with Federico Nuevo, which is to simultaneously use all the three-dimensional tomographic reconstructions to do a joint analysis not independent diagnostics of electron density or temperature or iron abundance, but to draw all of that single joint analysis of all the products. Before doing that, we have a plan for that. We have set up already some formally some codes for that. We really need to bring all these different products to a good consistency level, right? Before feeding all of these data at the same time to a single tomography technique. So that's pretty much it. So thanks a lot.
Thank you.
Just leave this last slide. Just a few numbers on, as you know, in Argentina, or maybe not, in Argentina, science is organized through a centralized organism called CONICET, which is the National Council for Scientific Research, Scientific and Technological Research. So that runs at the federal level science in Argentina. And so I put some numbers here concerning CONICET, the University of Buenos Aires, just to show you some.
Thank you very much.
Thanks.
So now
I
it's
probably
open
talked
for
too much.
questions. So anyone from the room or from online?
I have a question.
Yes.
Well, we talked earlier about those regions that are black because, for various reasons, but one of them you commented it could be because of dynamics.
Yes.
Has anybody ever used tomography and looked at where it didn't work to get a way of diagnosing the regions on the sun that were dynamic?
I mean, we usually avoid those. We avoid those.
Right.
We totally avoid those regions.
But I'm just thinking it's a way of pulling out the regions which are dynamically evolving in maybe a long-term kind of way over many data sets. Just the thought.
Yeah. What I should mention now that I see Rich here in the audience is Rich is proposing to pursue this neural network SLT to address the issues of dynamics. There are, I mentioned during my talk, there are schemes of time-dependent tomography that do not provide results so far that are far superior to static tomography. They can be superior. It depends really, I guess, in the specific period that one analyzes. So in this proposal, so the idea is to use simulation of tomographic reconstructions using time-evolving dynamic models, producing static images that correspond to an evolving structure. If you then use those synthetic images, you will not reconstruct you will reconstruct the model, but with artifacts to dynamics. But that needs to be done yet. So if that gets funded, I would say we can do that. That would be great. You can think of that as a post processing step. So you will do your usual tomography, and then you could use a neural network algorithm informed by all these pairs of data points to try to fix as much as possible the dynamic induced artifacts.
Yeah, you had a slide about temperature structure either increasing or decreasing with height.
Yes.
Those were around minimum. I'm just curious, at phases of the solar cycle, are one type more likely to erupt, resulting in CMEs, for example? So the low beta, there's more likely to erupt, for example, than the high beta.
I really want to know. What I can tell you is we have found this seems to be a possible structure, stable structure in the sun, in the core of streams and solar minimum. That is what we found. So it seems to be unrelated to CMEs.
Well, I think the down loops might be more susceptible to forming coronal condensations.
Okay.
Right?
Yes.
So because along the loop, the temperature goes up and it has a dip and then it comes back down. And along those dips, though, that's where condensations can form and maybe split it into two loops if it's that stable.
Right.
I don't know if you've seen that.
No, not really. I mean, and we haven't really, we want to revisit this analysis for the last, this is for the previous video. And it would be nice to redo this type of analysis for the last using AAA data. In principle, we have seen those downloads already, the data close to minimum, but we haven't done a analysis as a function of that yet.
You had the one slide where you were showing like the fitting of the local EM
Yes,
with different functions.
yes.
So I was wondering, since you do it like in a local space, do you assume that for a grid solid you still have like a multi-thermal plasma that you would fit, or because I would kind of expect that you have like one exact temperature and density at that
No,
point,
actually,
rather than
no.
distribution.
The best we find, it's always a distribution. There's that's a systematic result of DMT. That no, to explain the observed emissivities in using either 3 bands or 4 bands, we always need for some distribution. That's the best that works. Yes, not a single temperature, and that our interpretation of that is that you have a cell, a tomographic cell, a volume in the column that is threaded by multiple field lines where you have strong, transport is inhibited across field lines. So this is probably, to us, our view, this is giving you a measure of the characteristic temperature and density in that collection of field lines that are threading that volume.
Interesting.
While you're showing this, it was kind of surprising to see that the two normal distribution on the next slide, the blue ones, they did so much better than something with more free parameters like the four normal.
Yeah, that didn't work. Yeah, that's
kind of, do you have a feel for why?
No, not really. What I can tell you is this score R is a measure of score R0 is perfect for production of the 4 emissivities. The lower the score, the better the fit. Then the next one would be this asymmetric top graph. This is just showing a cell that has all plasma on the lower temperature edge, on the higher temperature edge. When you move to hotter regions, you might find in some regions the second component to be more dominant, and then this asymmetric top graph with change slope, right? We should ask Federico. I don't know if Federico is here, but he was in charge of exploring this, and he might have a better idea. Yeah, you're right. That for normal,
You'd think that would be able to do everything that you want to do and more.
it might have, I don't remember that right now, but it might be related to the 3 parameters. Some, in that 4 normal distribution, some of the parameters need to be fixed. I believe probably the centroids to match the top sensitivity of each band or something like that. And so it's kind of tricky. Yeah. Yes.
So you use kind of an expression for the tomographic reconstruction, and so like, is there the same expression for the emission pressure, the emissivity, or the DM, or the density, or you do have different expressions for tomographic reconstruction for different quantities?
Let's see. I'm not sure if I fully follow the question. So probably we are around here.
Yes. So like this is for the DEM, but like you for the where you show like how you actually perform the tomographic reconstruction. I guess that expression looks something like a linear regression kind of a model.
Oh, there's no model except it's purely the solution of this linear, least squares big problem. So yeah, it's a multidimensional unknown, and it's basically finding the set of X values, which are, let's say, the electron density or the emissivity in each voxel that best reproduce all the images while at the same time having a smoothness property. Yeah, but there is no parametric model whatsoever there. If you will, the only parameter is this lambda, which is the amplitude of the regularization. And there's a specific procedure to find the optimal value for that, which is called cross-validation. But that's the only parameter, really. But other than that, there is no ad hoc model.
Okay.
We've heard of the tomographic reconstructions of CMEs from just 2 or 3 points of view, and maybe simultaneous observations. But then, for that specific problem, you probably introduce some model for the CMB with some parameters, and what you hope to do is to reconstruct the value, the optimal value of those parameters. But this has no model built in.
Okay.
I'm guessing the regularization has a different form for PB versus emission versus all the different types. Of
Right now we are using a smooth derivatives. Yeah.
Oh,
That
okay.
is, yeah. In this case, no, there is not much of a change.
Okay.
Yeah. Yes.
I was wondering what limits basically your current resolution, or phrase it differently. Is there a way to increase the resolution? Like if you would have like a higher result, like observation, could you get like smaller details out of the SRT?
I believe we are at the point that we really do the opposite. We bring down the resolution of the image. We rebeam the image because actually it's an interesting question. The grid resolution is also related, for example, to the cadence of the observations. And there's a link for that. One could think, okay, I will use all the cadence possible, but then you will introduce a lot of dynamics into feeding the reconstruction, which is something you don't want. I mean, if you increase the cadence, you will be feeding your tomographic inversion probably with faster and faster dynamics. You want to avoid here. Now, given a specific cadence, then your resolution shouldn't be too thin, can be too thin. Your grid cannot be too fine, because then you will be missing data. You will have too little data. And so just to give you an example, for PV instruments, we typically use one image every 6 hours, something like that. And then the grid that we're using, which is 2 degrees, is right enough. If you increase the resolution or you lower the resolution of the grid, that won't be consistent with the cadence on one end and with the resolution of the image. The reason, for example, we reveal the image is because we don't want to have, if we just use the full resolution of AAA, for example, we will have each individual tomographic cell will be threaded by, imagine a cell in the plane of the sky, it will be threaded by tens of lines of sight, and that's just replicating many times basically the same equation. And the other end, of course, is too loose, right? To have too few lines of sight. So there's an interplay between the resolution of the grid and the resolution of the images. But I would say that you don't want to increase your cadence too much, because then it will be introduced in dynamics. The tomographic inversion like this can only will invert based on the information you get. If you're giving too much information, like let's say one image every minute or so, you're introducing a lot of dynamics, and your reconstruction will be severely damaged. if we had a lot of spacecraft. That would be great. Right then.
Any other questions? If not, then let's thank our speaker again.